Yes, hello, University of Idaho students, Dr. Shish. My name is Robert Bolaños, and this is actually my presentation for our final project, which I have actually called it as Dipole Antenna Simulation. So to kind of get a little bit of a preview about what to expect within my project, though, here is my table of contents, and these, as you see right here, are actually the topics that I pretty much would like to cover within my presentation. So the first thing that a non-specialist would ask is, what is an antenna and how can it be used in communication systems? That is the answer. That is the question. Here's the answer. The antennas are pretty much devices that converts radio frequency RF fields into AC currents and vice versa. They are constructed with the use of metallic conductors with an electrical connection to receivers or transmitters. Current is forced through these conductors by radio transmitters to create alternating magnetic fields, and these fields causes induced voltage at the antenna terminal, which are connected to the receiver input. In the far field, on the other hand, the oscillating magnetic field is coupled with an oscillating electric field, which defines the electromagnetic waves that are capable of transmitting signals for long distances. So antennas, they play a vital role in communication systems because they can be used in both the transmission and reception of radio frequency signals. And to kind of get a better understanding about what that concept means is utilizing wireless antennas, because they're actually the perfect example, because some of their roles that these antennas serve in today's communications are very vital in today's society. And these roles include that they can transform signals into free space and vice versa. Second, these wireless antennas can vary in terms of design, size, and performance, which actually gives the customer or consumer various of options to choose from. Third, Wi-Fi antennas, they can actually easily be upgraded to improve. They can be easily upgraded to improve its performance due to its increase in business productivity. Which is why signal boosters, they're no longer needed anymore, because these Wi-Fi antennas, they're high quality antennas that can provide the service that customers really need. And the last final thing is that they're a lot easier to set up than the old-fashioned way. So our project that we were assigned for today was that we had to design and build a simple portable system to visualize in easy way the properties of an antenna system and provide educational material to explain these properties to non-specialists. And these were the following properties that we had to choose from. And for me, what I decided to do was I wanted to kind of base it off of beam widths and antenna gain. So the first thing you would ask yourself is, what is beam width? Beam width is actually the aperture angle as to where most of the power is radiated and are located between the points in the main lobe that are located down to the maximum gain by 3 dB. And normally these beam widths, they're actually associated with other beam widths, and which as you can see right here on this chart that I have, and these beam widths are the half power, and the first null beam widths. So the difference between those two is that the half-power beam width is defined as the angle between the two directions where the radiation intensity is pretty much 1/2 of the main beam. The first null beam width, on the other hand, is defined as the angular separation between the first nulls of the radiation pattern on its major lobe. And one of the major important aspects of this presentation, which you will see later in the FEFCO simulation results, is that beam widths can actually be controlled or changed depending on various methods. And one method is that you can actually increase what is called the aperture distribution, because with the larger aperture, this results in narrower beam widths, which can reduce the elevation coverage of a radar or an antenna, and this effect can only happen by increasing or decreasing the antenna dimensions, which you will see later on in the presentation. Another method is to increase the wavelength, because the intensity of the reflections will be reduced, but the width of the lobe will be wide enough where the beam width will start to increase. That is if we're assuming that the aperture size remains the same, of course. So antenna gain, which is also known as the power gain, describes how much power is transmitted in the direction of peak radiation. And on both sides, from an antenna perspective, from the transmitting side, the antenna gain describes how well the antenna converts input power into radio waves, where those waves will be directed in specific directions. Whereas on the receiving side, this is where antenna gain describes how well the antenna converts radio waves that are arriving from a specified direction into power. And the antenna gain can be controlled just like beamwidths can. They can be controlled or calculated based on the beamwidths, because as mentioned before, in a transmitting antenna, the antenna gain describes how well the antenna converts the input power into radio waves in specific directions. This implies that the gain describes how narrow the radar beam is. So in other words, if you have a higher antenna gain radars, they can easily create narrow beam widths. For lower gain antennas, that's where you're going to create wider beam widths. So if you was to ask yourself as an engineer, like, what would be a best performance case that you would want your radar or an antenna to perform, like what would be the best ideal case to do this, you would really want to narrow the beam widths, and that is pretty much beneficial for us as an engineer, because if we were to narrow the beam widths, then your antenna and radar, they're going to have better range resolution, and you're also going to have detection range. And what that means is that radars and antennas, they're out in the real world applications, they can actually detect out targets or objects that you see out in the sky. They can, with those things, they're able to seek out targets and objects very efficiently though here. So it's better to have, so it's really, really beneficial though here for a better performance case that you narrow your beam widths as you can though here. So antenna gain is not the only thing here that we also have to work, that is also a concept in radars. The other gain that is also a concept is called realized gain. And this gain is defined as the mismatch losses of the antenna's input impedance. And this gain will also be less than the power gain, and it will be calculated by considering the total efficiency of the antenna along with its directivity. The total efficiency of the antenna is considered as the losses due to the reflections at the input terminals, as well as losses within the structure of the antenna. And so the total efficiency formula, as you can see, is pretty much this equation right here, where this term right here is the reflection mismatch efficiency. This term right here, this is actually the dielectric efficiency. And then you also have the conduction efficiency. And the dielectric and conduction efficiencies are usually grouped since they are measured and are known as this term, And the total efficiency may now be written as this equation, into this equation. Therefore, if you was to calculate it by using the total efficiency and the directivity, that's where the realized antenna gain formula is known as this equation right here. And therefore, realized gain and directivity are specified in dBi, that's the unit of measurements, and the voltage reflection coefficient in dB, and the efficiency as a value between 0 and 1 is. So for my radar design, thanks to FEFCO, I decided to construct a half wavelength dipole antenna with a half wavelength of about 32.5 millimeters long, a wire with a wire radius of about 0.1 millimeters, and it's operating at a frequency of about 2.4 gigahertz. As mentioned before, with a larger aperture distribution, we can have narrower beam widths and results in a huge increase in antenna gain. So this can only happen by increasing the antenna dimensions, increasing or decreasing the antenna dimensions. In this trial experiment that I'm going to be showing here, I'll be showing you the results if we were to change the values of the length, which is pretty much this 32.5 millimeters. So this first trial that I'm going to show you will demonstrate the results by using a length of 32.5 millimeters, and then there's also going to be a second trial that I'm also going to show you, and this is going to be, and that second trial is now we're going to increase this length to a certain value, and from there, once I show you the results, you're going to see the differences when it comes to finding the peak intended gain, the peak realized gain, and the half power beam width. So the first experiment that I did was I did calculate the half power beam width with FEFCO, and the results that I found out was 86.5604 degrees. So for my peak intended gain, I'm able to get a peak intended gain of about 1.86249 dBi. And for my realized gain, the maximum I'm going to get is negative 17.0526 dBi. So that was the first simulation. Now, this is the second trial experiment. So this time, we're going to increase the length to about 72.5 millimeters. So now that you saw the results from the first trial, let's check out what will happen when you increase this length. So if you look at the half power beam width, you notice that initially at first it was 86.5604. Now I have it at 73.3621 degrees. So it's gotten narrower. So for my peak intended gain, it actually went up. And this is where you get 2.3 2444 dBi, so you see an increase in peak intended gain, and your realized gain will pretty much also increase in value, not as far as like minus wise, but it's going to be increasing by negative 2.1374 dBi. So based on the trial simulation results, all of those parameters can be achieved based on the relationship between antenna gain, beam widths, and dimensions, which is pretty much the main lesson that I've really learned a lot, not only in researching, but also even experimenting in FEFCO during my free time. But I have learned that higher antenna gain raters can create narrow beam widths, and lower antenna gain raters creates wider beam widths, as I mentioned before. But the key concept I've always learned is that the narrower the beam widths, the more that the radar and antenna will perform at its best as a best case scenario. And the difference between the antenna gain and the realized, and also the difference between the antenna gain and the realized gain was also an interesting topic that I have learned, because to be honest, I've really never known what realized antenna gain was used for and how it can benefit the antenna in a way of its performance. So I thought that was pretty amazing though here, to be honest with you. I also think that this design could be added on for any future plans. I really do, because it really depends on the parameters that you're given in the design. Because at times lower frequency radars, in most cases, not all cases, they'll have bigger transmitting antennas compared to high mid-range frequency radars in order to get narrow beam widths. So therefore, knowing the parameters and the designs and what you're trying to achieve is also critical for any future plans if this design is willing to exceed on any worth. Alright, this concludes my presentation. Thank you so much for your time though here. Hope you enjoy it. Thank you.